Last, some of it we talked about a little bit, but for the most part, most of it didn't show up on the exam. It only showed up in a limited part. So number one, percents. These are unitless pieces of information. Right? So if you get a 90% in the class, what is the unit on that? Or isn't a unit. All it means is that you got 90 points out of a possible 100. But that could have also been 900 points out of a possible 1,000. Okay? The percent removes the scale of our system. Right? So what it's trying to do is standardize our reporting. Right? So if you went through and did an experiment, in that experiment, you were trying to isolate gold from some dirt, and you obtained 5 grams of gold. I did that experiment as well, except I obtained 5,000 grams of gold. Okay? We now report that data to our supervisors. Our supervisors are now going to mine whose gold or whose dirt, your dirt or my dirt. Remember, you got 5 grams, I got 5,000.
You did. Everyone.
Okay, they're going to want to mine my dirt. To get that 5,000 grams of gold, I had to dig through 20 billion pounds or 20 billion grams of dirt. To get the 5 grams of gold that you guys did, you dug through 6 grams.
Then they're going to go through mine.
Oh, they're going to go for yours. The raw data is useless. We need to have some context of where that data is coming from. If we had 5 grams of gold in your 6 grams of dirt versus my 5,000 grams and I don't know, we'll just add a bunch of zeros. We can now see that your sample has a lot more gold per dirt. That means more money, okay, less work. Mine, yeah, I got a higher amount of gold, but how much stuff did I have to dig through to get it? A lot more. That makes mine not very worthwhile. Okay? So what we would report out is not the raw value, but the amount per possible sample. This is a percent. That's all a percent is trying to do. So you're taking the amount of whatever it is and the total sample where it came from. You multiply that by 100, we now have a percent. That's what we will report out. It's a way to standardize our results so we can compare your experiment to mine. Kind of make sense? Okay. Really, all it is a conversion factor, because I now have a quantity per something, right? Like miles per hour. It's another conversion. So how can we go through and use this? So bronze is an alloy of copper and tin. A sample of bronze contains 79.2 grams of copper and 10.8 grams of tin. What is the percent copper in bronze? So there's 2 questions there, so let's answer the first one together. So what answer do we want?
Percentage.
We want the percent, and I heard someone add the extra important part, percent of copper. Okay? To get that, that's why I have this formula. Okay? Which is kind of annoying to have to use a formula, but it's easier to deal with that for percentages. Okay? I need to know the one quantity. What is the one quantity I'm looking for here? So we have 2 values that we could use. We got 79.2 grams of copper, and I have 10.8 grams of tin. What is my one quantity in that equation, this term? It's my copper. So it is my 79.2 grams of copper. Right? And I always forget to times by 100, so I'm going to put it out front. What is the total sample? Okay, I hear 90. Nowhere there do I see 90. What if we had said 10.8? 10.8 grams of what? Tin. How much tin, or how much copper is in tin? Nothing. It doesn't make sense. What we're looking at is our total sample. It's the alloy. And our total sample is going to be the mass of copper plus the mass of our tin, which, was it really 90?
Yes.
We can now enter it into the calculator, punch some random numbers, and I think we come out with a number that is roughly 88.0%. Questions?
If you said
Make sense?
Roughly 88%.
88.0%.
Okay, that's
By roughly, I was actually saying what the answer was. It is 88.0. How many sig figs in the answer?
2.
3. The 0 counts as a sig fig because there's a decimal point, there's a sig fig in front. Okay. Why do I carry 3 sig figs? How many sig figs in 79.2?
3.
Sig figs in 90. Sig figs come out 3 all the way through. Make sense? Your turn. How much tin is in 100 grams of bronze?
I feel like I did.
So we want the grams of tin as the final answer. Well, the grams of tin come from our alloy of sample. Okay, so we could say we had 100 grams of our bronze. Are you okay with that? That was an awful lot of letters. That didn't really shortcut anything. Okay, but the issue there is, are grams of bronze the same thing as grams of tin? No. So what do we need? Conversion factor. In that conversion factor, what do I know has to show up? Grams of bronze. Where should the grams of bronze show up in my conversion factor? On the bottom. What unit do I want to show up on top? Grams of tin. Okay. Do I have that conversion factor? We can figure it out. Okay? It is not explicitly given to you. Okay? Do we know the grams of tin?
No. We knew from the previous question.
If we use the previous context of the information, because that explains to us an alloy. What alloy? Bronze. Oh, so that gives us information about the bronze. Do we know the mass of bronze in that previous question?
Yes.
What is the mass of bronze?
90 grams.
Do we know the mass of tin?
10.8 grams.
In that sample, I have that information. If I then multiply by my 100 grams of bronze, what happens to units of bronze? Cancels, and I'd be left with grams of tin. That works. Was there another way to do it? Yes. There's always another way to do it. What did the first question get us for an answer? 88% what? Of copper in bronze.
So at least 12%.
So that means that there's 12% tin in bronze. Because it's bronze, it will never change. That is the sample. That's by definition what that means. What does 12% mean? It is 12 per 100 . Okay. There are 12 grams in 100 grams of sample. How much sample do we have?
100 grams.
That shouldn't say percent. Sorry, that was my bad. What do we get as an answer?
12.
12. What happens if we take 10.8 divided by 90 and multiply by 100? Amazing, we get 12. Either way we do it, we get the same answer. So there's different formats for how we can get there depending on how we see the information and how we want to solve our way through it. This is one of the things that becomes challenging within conversions. What we will talk about in class is likely one way to solve something. Sometimes if I feel it's important enough, I'll show 2 ways. Were there others? Yes. Okay. Did you see another way? Yes. Did it work? Did you get the right answer? That's your check. Now do a whole bunch more questions. Do you consistently get the right answer? Then your method is valid. If you don't consistently get the right answer, your method's not valid. Okay? And you need to switch. Kind of make sense? Okay. Volumes. Volume comes as a measurement because we have liquids. And liquids are not easy to kind of mass or determine their kind of characteristics. So we invented the term volume. Okay? The easiest way to look at a volume is looking at a cube. And when we measure the volume of a cube, how do we determine it? Length times width times height. So what is the length unit of the volume shown?
10 centimeters.
So the volume of that cube, we said was length times width times height, and I'm hearing that the answer is 10 centimeters. 10 centimeters cubed. You're saying no, why?
Because that's only one thing, so it's not all.
This is where it's helpful to actually write out each step instead of saying, well, I'm just going to throw a cubed in there and fix it. Because that cubed is not applying to just the centimeters. What is the length? 10 centimeters. What is the width?
10 centimeters.
What is what's the other one? Height. When I enter that into the calculator, that is 10 times 10 times 10, which is 1,000 centimeters cubed. This is where volume becomes tricky. Because we go, oh, well, I know it needs to be cubed, so I'm just going to say cubed. That cubed applied to the entire thing, not just the unit. When we now go through and look at our answer, it's now only applying to the unit. So we have to be careful with our notations to make sure we don't lose track of what's happening with our meaning. Kind of make sense? Can you say that unit for me? Centimeters cubed. Centimeter begins with C, cubed begins with?
C.
Give me 5 cc's stat. What's that cc that they're talking about in medical terminology? Centimeters cubed, also known as a milliliter. Okay? How do we know it's a milliliter? Well, that's an interesting question, Mike. Why don't you show us? I know we have 1,000 centimeters cubed. I want to get this into units of milliliters. How do I do that? Well, I need to get rid of centimeters cubed, and ideally I'd go into milliliters. Well, if I knew that conversion, I wouldn't be solving this. Come on, Mike, that was a dumb question. What can I get the centimeters cubed into? Well, this is the definition of a liter. So, 1,000 centimeters cubed is 1 liter. That is the definition of a liter. Are liters the same thing as milliliters? No, so we need another conversion. What is the conversion between milliliters and liters? Milli means 10 to the negative 3. Where does our power of 10 go? With the core unit. What happens? Oops, I said centimeters. Said 1 centimeter cubed is how many milliliters? Anybody got a calculator? I was asking for centimeters cubed to milliliters, so it was 1 centimeter cubed to start with. It didn't make sense to start with 1,000. All right, you didn't enter that in the calculator yet? What'd you get? Is your calculator broken? We started with 1. No, your calculator's not broken. It is 1. What is 1 centimeter cubed? 1 milliliter. That's why they're using that CC unit. They're using the distance measurement of volume. So we'll have a volume measurement for volume and a distance measurement for volume. Depending on the context of what we're working in, we may choose one unit over another. Okay? Our base metric unit is a liter. It is defined as the volume of a cube that measures 10 by 10 by 10 centimeters. Okay? That is now a definition, which means how many sig figs? An infinite sig fig count. Okay? So we just did that. So here we go. Here's our trap. An automobile engine displaces a volume of 498 centimeters cubed in each cylinder. What is the displacement of a cylinder in cubic inches? Does anybody have an immediate question that they want to ask before attempting to solve that on your own? Okay, conversion factor. I will give you one conversion factor, and it is not of your choice. I will tell you that 1 inch equals 2.54 centimeters. You now have all of the context you need to go through and solve this. Tell me what the answer is. What are we looking for? Equals what? What are we given? And we're given some kind of conversion factor. So we'll give it a shot. We'll see what happens. So, centimeters cubed is not inches cubed. We need to get rid of the centimeters unit. So that centimeter unit should show up where? On the bottom. What should show up on top? Inches. Now the question associates are the numbers with those. Okay? And we could even say, well, I want centimeters cubed and inches cubed. Okay? Because that's the ideal scenario, right? Okay? Do I have a conversion factor between those? As centimeters cubed and inches cubed? No. What I'm given is inches to inches to centimeters. I know 1 inch is 2.54 centimeters. But I want it cubed. What's wrong with that? It's going to come down to the meaning of that cubed. What is that cubed referring to? As it is written, it is only referring to the unit. The conversion factor is not 2.54 centimeters cubed is 1 inch cubed. Okay, the conversion factor is 1 inch equals 2.54 centimeters. By writing that cubed, you're falling into the distance volume conversion trap. Okay? It can become easier to not fall in that trap if we slowly process this out. We know that conversion is valid. What would our units be if that was our calculation? So I'm still getting some people who will say, well, that's now inches cubed. What would you get? If that was just centimeters, then that would convert to inches, but I still want inches cubed. Okay? So some people said, well, it's now taken it to inches. It may very well have taken it to inches, but it's inches cubed. Okay? What does centimeters cubed mean? Hearing a lot of people said, well, those cancel. Okay, let me give you 10 cubed dollars. If I give you only $10, are you going to have a slight objection? Yeah, because 10 cubed is not $10, it's $1,000. That cubed means you do it 3 times. What does the cubed next to that unit mean? There's 3 centimeters. This only cancels 1. How can I cancel the second? I can do it again. And again. Now all of the centimeters cancel, and I would end up with inches cubed. And this is where we say, well, aren't you just repeating that calculation? Couldn't we have simplified that down to just an exponent? Yes, but it's still a question of how did you simplify that down to just, that says centimeters, an exponent. Whoa, can't speak or write. What good am I? Take me back to the farm. That was a joke. Hopefully none of your parents told you that your dog went to the farm. Cubed. That cubed applies to everything within the parentheses, also known as saying 1 cubed, inches cubed, 2.54 cubed, centimeters cubed. Now you've got it in one short step that you can convert across. But you had to realize the power of the exponent. The exponent must translate through all the way to the number. If you aren't translating it through to the number, when you enter it into the calculator, you get the wrong answer. Make sense?
Could you have just multiplied 498
By 1, by 1, by 1.
by 1 divided by 2.54 to the power of 3?
Yes.
You put those in parentheses?
Yes. So it now comes down to how do you want to enter it into the calculator. And there are a variety of ways to do that. If you want to go through that details with me, that's fine. It's not a calculator class, so we won't go through that because everybody has a different calculator. Okay, but if you want to learn how to put that in the calculator, you can talk to me after class and we'll do it.
Like on the test, do you have to show you like each, like the one?
So on the test, what gets credit? The ones colored below and the ones, or both of those get credit. What does not get credit? And I'm now out of space. Let's write a not credit one up here. On a test, if you wrote 4.98 centimeters cubed times 1 inch cubed, 2.54 centimeters cubed. Because that does not equal the official answer. 16.3 is the 2.54 cubed. That is okay, because you've done the calculation. Just kidding? Okay. We good? All right, so watch out for that trap. It happens every so often. The answer was, what do we say, 498 divided by 16.54, 30.3898, I believe is what the calculator spits out. And I could be wrong on that. I did just do that in my head. It was kind of a rough one to pull out. 8. How many sig figs? 3. First insignificant. Our answer becomes 30.4 inches cubed.
Since 498 doesn't have a decimal after, does that make it infinite?
No. The decimal only applies to deciding what's going on with the 0. You'd have to be told that it was exactly this value or defined as this. That's a measurement. You guys impressive with that head calculation? That's pretty awesome. Maybe that secret will get revealed later. I'm pretty awesome at that. Volume, irregular versus volume of irregularly shaped objects. If we have a square, we can measure length, width, height. If we have a rectangle, length, width, height. If we have a sphere, what's the volume of a sphere? Pi r squared. Is that right?
I think it's 2 pi r
2 pi r squared. Volume of a sphere, you can talk to your geometry, trigonometry instructor, and they can help you out with that. One of those math type things. Okay? So we can figure out the volume of regularly shaped objects. But what happens if we have this weird stabby object up here? Okay, well, we could approximate it and say, well, there's a triangle there. I can measure the volume of that triangle, the volume of that one, and 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 that one. And then it's roughly an oval, and I can measure the volume of that oval through a calculation. I can add up all those volumes, and I have the volume. Sweet, that sounds like fun. I don't like that. Okay, but we could do it. What about that guy? That's going to be a bit rough. Okay, and what are we trying to show in that picture? It's really hard to get a picture of this, by the way. Gas. How do we get the volume of a gas? It's an irregularly shaped object. It moves wherever the heck it feels like. How do I get the volume of that? Right? So we run into ways where we can't measure these volumes nicely. We need some other process. Okay? To do that, we can use an object and look at its volume in a liquid. Because an object will displace an equal volume of liquid. This was the whole Archimedes principle. Archimedes, the Eureka guy, sat in the tub. Eureka! I know how to determine gold. Good for you, dude. Get back in the bath. Or put on some clothes. Okay? An object will displace an equal volume. So if I take a look at that jade sample, at least your textbook calls it a jade sample, which is that green thing in the water there, and I want to know the volume of that object. Well, I can take a graduated cylinder with some water in it, 50 milliliters of water to be exact. When I drop the jade sample in, it's now going to push the water away equal to its volume, which then means the volume increases to 60.5. Well, what was the volume of the jade then? Subtracts 60 or 50 from 60.5, and we now have the volume of the jade to be whatever that is, 10.5. Okay? So we can do volume measurements by displacement. We can do the same thing with gases. If I've got a reaction flask with a gas in it, okay, or I've got a reaction with a gas, and that, by heating it, now causes a gas to form. The gas can rise up through this container, and it will then fill whatever shape it's occupying. It can fill this shape, but it's now putting pressure on that liquid. So what happens to the liquid? It then rises up this other little tube and collects out here. I can then measure the volume of the liquid change out here. That will correspond to the volume of the gas. Kind of make sense? One massive issue with that. Anybody take a balloon and put it up near a fireplace? What happens to the balloon? You do it slowly and carefully enough. Before it pops, what does it do? It expands until eventually it weakens and then it pops. Okay? What does that mean? What does heat do to pressure or do to our gas particles? It makes them move more, which makes the volume change. When we're measuring volume in this way, we want to measure just the gas, not the effect of heat as well. What's the problem, though? How are we getting the reaction to happen? We're adding heat, which means we might be monitoring a temperature change, not just the gas change. How do we prevent the temperature change from being in effect? Make this tube stupidly long and far away from the heat. What does that mean? That means the gas will have cooled to room temperature by the time it gets to the place where we can measure it. We don't have to be worried about a temperature effect on it as well. Okay? Just kind of a nuance in science there. Sometimes we got to be careful. Okay? Last big one, density. Okay? It's an intrinsic property of a material which allows us to identify it. Okay? And where density becomes interesting is that if we say, took which weighs more, a pound of lead or a pound of feathers. So you could take little kids and point and laugh and, no, they weigh the same. because it's a pound. I'm so much smarter than you. Right? Because almost always we'd say the lead, right? So the weight's the same. Why are we saying the lead almost universally instead of saying they're the same? Okay. We're thinking more towards the density of the material potentially. It's actually a big psychological nasty experiment. But it's really, or part of it goes back to the density of those materials. Okay? So one possible explanation for why kids don't understand this is they don't understand the difference between weight and density. Because they are related to each other. Density is a measure of the mass of the object, effectively the weight, with respect to its volume. Okay, so that's going to change for an individual material. And when we look at lead, lead is a much more dense material. It has, we look at a pound of each, they have the same mass, but the volume of lead is going to be much, much, much smaller, which means when getting hit with it, it'll probably hurt a lot. Okay? It's how that weight is displaced across it. So what is now special about our density? It's a mass per volume, miles per hour, quantity per sample. What was that?
It's a conversion.
It's a conversion factor. Okay? That's why it's showing up here. Okay? So we now need to be able to use it and apply it as a conversion factor. Depending on what species we're looking at, we may see different values for the density. Because the value might change, we might also change the unit. If we take a look at ice, your density measurement is grams per centimeters cubed. If we look at water, it's grams per centimeters cubed. When we look at water vapor or the gas phase, would we expect to still use grams per centimeter cubed? Why not?
We can't measure that.
We can measure it. Why would we not use grams?
Too big a measurement.
It's too big a measurement? The mass of gas is higher than the mass of ice or water? Too small. The units now shift to such a small value that it monkey, I thought the number was there. That if we said used grams, we'd be looking at 0.00003 arbitrary number grams. What's the issue with looking at a density with that? That involves a lot of zeros. We say, oh, okay, well, I'll simplify it. I'll make it 3 times 10 to the 1, 2, 3, 4, 5. -5. So now I don't have any more zeros, but now I have an exponential power. And we all love exponential powers. Okay? So what can we do? Well, instead of looking at it as grams, we can look at it as milligrams. What happens? Well, then that gets rid of a bunch of those zeros, and it becomes an easier number for us to process. And pretty much everything we do is about trying to make numbers easier to process. So we'll change the unit on that. How do we interpret our densities? Okay. If we take a sample, graduated cylinder with 3 different liquids and 3 different solids, they will all partition out according to their densities. What can you tell me about solid number 3? It is the highest density. It is the largest density. That's why it's at the bottom. Solid number 1,
Least dense.
the least dense.
Well, second least.
Second least dense, it's the least dense of the solids, but it is more dense than
The first liquid
the first liquid. And we know that because
sitting on top of the second liquid.
solid number 1 is at the bottom of liquid number 1. So solid number 1 is more dense than liquid number 1. Kind of makes sense? We've got our variety of densities for different materials listed out there if you really wanted to go through and look at those. Do we need to do a conversion factor with density?
Sure.
I heard a no first, so let's see if we can compromise. We'll compromise. We'll skip the first one, we'll do the second one. An automobile battery contains 1,275 milliliters of acid. if the density of a battery acid is 1.84 grams per milliliter, how many grams of acid are in an automobile battery? Just like every other question, where do we start? What do we want for an answer? Grams of acid. What do we want to start with? Ooh, we're given two numbers. So now things become a little bit trickier. Which one do you want to start with? I heard 1,275. Where should the 1,275 show up? In the numerator or the denominator? Why the numerator?
Because you have to cancel out milliliters in the next step, which has to be in the bottom.
Right, so you're saying it belongs in the top because I've already done the calculation. I don't quite accept that.
It's over 1.
It is over 1. What's that? So every explanation I've been given is because you're telling me that when we use the conversion factor of putting grams of acid, 1.84 grams of acid, 1 milliliter of our acid, you're saying because of this conversion factor, the conversion factor that we didn't write yet, remember, you said you wanted to start with 1275. So because of the conversion factor that I didn't use, I want to put it on top. I don't know that I like that explanation. Okay, so one quick answer. Screw you, Mike. Fine, we'll start with the other. Okay. I would probably argue it's easier to start with this one because that has the answer unit that we want. It has grams of acid. Okay. We want to place the grams of acid where? In the numerator, because where does grams of acid show up in the answer? In the numerator. Okay. Do those equal each other? No. So, what do we need to do? Cancel the milliliters of acid. Am I given the milliliters of acid? Yes. So I'm not saying you were wrong by placing the 1275 milliliters of acid in the numerator. Okay? But you didn't give me a very good reason for starting with it in the numerator. Okay? And this is one of the questions that you will encounter when you don't know the units, is you won't know where to start. I think it's easier to start with a unit that you know you want in your answer, place that where you want it to, and then start to cancel stuff out. If you don't know, find something that compares. Why would I place 1275 milliliters of acid in the numerator? Well, milliliters doesn't show up in my answer, but what does? Acid. Where do I want acid to show up in my answer? Numerator. So where should I place that acid unit? In the numerator. So it's not so much for the measurement value, but the type of value. Right? Both work. It's whichever floats your boat. Okay? So there's our conversion. So we satisfied the do one and we satisfied the do not do one. Good? Which gets us to temperature. Temperature is a measure of the average kinetic energy for individual particles in motion in whatever sample we're looking at. Okay? Conveniently, the measure of kinetic energy or the average kinetic energy for an individual sample is something that was done in a variety of different locations around the world at various times, and officially roughly the same time. What does that mean? Well, Jamie's decided that the unit she wants to use to measure temperature is going to be Fahrenheit. Good for you, Jamie. Angela, on the other hand, said, well, at the same time, I'm going to measure using Celsius. Then Jamie and Angela talk to each other. Say, well, I'm measuring using Fahrenheit. I'm measuring using Celsius. Oh, we're measuring the same thing. Let's agree to get along and just use one of them. No. Didn't work like that. They yelled and fought with each other. Eventually they built up enough teams that those teams then decided, well, we're not going to use that, and we now have 2 temperature units. Okay. Then along comes science, ultimately mathematics and physicists, doing some fancy mumbo jumbo with energy and calculations and reactions. And they said, well, neither of those terms make any sense, so we're going to invent a third because mathematically we need a third. There's Kelvin.
Should be in the same boat.
Okay? What does that mean for you as students? You get to convert all of them. Okay? So, common numbers. In Fahrenheit, a lot of these were based off of, actually I'm not sure it was water. Fahrenheit, your freezing temperature was decided to be 32 degrees Fahrenheit, boiling was 212. Because 212 is a little bit more than 100, and more is always better. Why 100? Well, because Celsius, the freezing point was 0, and the boiling point was 100. So as soon as we established those, that's how they went. It's probably a little more sciencey than that, but close enough. Kelvin, our water numbers, your freezing point is 273 Kelvin, because they were like, screw you, Fahrenheit, we're going to be even bigger. Again, not really true, but close enough. And it boils at 373, sorry. Okay. There is a typo here. Notice that I have degrees next to those kelvins. There is no degree. Like there is no spoon. It wasn't that funny, it's okay.
There's no what?
Spoon. Kelvin is an absolute temperature scale, which means no degrees. Because Fahrenheit and Celsius are not absolutes, they're kind of approximations off of a standard, they get degrees. Okay? How do we go through and deal with the conversions? Well, if you want to go Celsius to Fahrenheit, it'll be your degrees Celsius times 9, because that's smaller than 10, divided by 5, because that's halfway to 10, plus 32, that's now Fahrenheit. 32 because that's younger than me. Okay? Why did we use these as conversion factors? People didn't get along. Okay? Your Celsius to Kelvin, you will always add 273 degrees Celsius, or 273. I happen to remember 0.15. You don't need the 0.15. I just happen to remember some random more sig figs, so I dealt with it. Okay? You are responsible for memorizing the 273 to your Kelvin. You are not responsible for converting Celsius and Fahrenheit, because it's just a dumb conversion to deal with. Okay? So I will give you the Celsius to Fahrenheit. I will not give you the Fahrenheit to Celsius. Oh, heaven forbid, it's algebra. Okay? If you need help with that algebra, I will help you with it, but that's all it is. I don't want to do those conversions, because they're straightforward. Let's bring in the heat. Temperature was a measure of the average energy. Heat is a measure of the total energy. Okay? They're related, but not the same. Okay? So heat is typically measured in units of joules or calories. Okay? You might say, well, what is the difference? Well, if I take an eyedropper full of 100 degrees Celsius water and squirt it at you, you might get a little pissed, but it's probably okay. We probably still get along. But if instead I took a liter container of 100 degrees Celsius water and I threw that at you, you're probably now really pissed and I might be going to jail. Okay? They're both the same temperature though. Why do you care? The average energy is our temperature. Heat is the total energy. That 100-liter container has a heck of a lot more total heat within it. That's going to hurt a lot more as that energy gets transferred into your skin. Okay? So heat and energy are related, or heat and temperature are related, but not the same. Specific heat is now a measure of an individual substance. Yes, we're done. The specific heat, and we'll start with this on Tuesday too. Crap, screw it. We'll just deal with it. I'll start with it on Tuesday.